Now, if you have watched any Star Trek or any similar sci-fi show like that, you know interference mainly as a plot device.
Too much interference.
The electromagnetic interference.
But the surface interference is distorting its position.
But we're running into a lot of interference. It's going to take some time.
It always happens right at the moment when you need to beam out.
Can you get a lock on the away team?
Negative, sir. There's too much interference.
But there's also actual physics behind interference, and in fact, it's one of the most important effects concerning waves.
There's just too much interference.
In short, interference is simply what happens when a wave hits another wave. The waves simply combine, but do not otherwise influence each other. Therefore, when the waves are equal but opposite, they will completely cancel out when they interfere. Wave plus wave equals nothing. If you have a wave signal and add another signal on top of that, the original pattern will be changed, sometimes severely. Noise will in some parts add up to your signal and cancel it out at some other points. So as long as the noise is there, the total signal will become distorted up to the point where it becomes completely useless. And that's exactly how interference can mess up your communication.
With all this interference, we might not get a positive lock to bring them back.
Or your transporter beam. Okay, so waves interact with other waves by simply adding up at each point. This is called the principle of superposition, and it's a very general mathematical feature of all linear systems. Waves are usually linear systems, described by a linear differential equation. The very wave equation we already talked about in the last video. Some wave behavior is nonlinear though, like water waves breaking near the beach. This behavior is more complicated than just adding up two waves at each point. What's the difference between interference and superposition? Well, you could say that the general principle and also the adding up, the act of adding up the waves is superposition. And interference is the result you get out of that. So either constructive or destructive interference, depending on the relative phase of the waves. If both waves are in phase, they oscillate in exactly the same way, and crest meets crest and trough meets trough, so they simply add up. Constructive interference. If the waves are out of phase, they do exactly the opposite of each other, and crest meets trough and trough meets crest, and everything cancels out. Destructive interference. Why is all of this even remarkable? Why do we need to make a video out of it? Because usually when two things meet, they do not simply overlay and add up. They collide. And waves do not collide like objects do, which is a reminder that waves are not objects. Waves are a form of motion. For example, the destructive interference seems logical enough to us for water waves. One wave goes up, the other wave goes down, and in total they cancel out. But there are other examples that don't seem so straightforward, even though the principle behind it is exactly the same. For example, it isn't obvious why two rays of light might cancel out each other, why light plus light might create darkness. But it's the exact same principle. Simply two waves adding up in a way that makes them cancel out. But it seems like as if 1 plus 1 were 0. In truth, it's of course more like 1 plus minus 1 equals 0, which is not surprising, but we just do not see the wave nature of many things like sound or light. Another significant example is two identical waves moving towards each other, which for example happens every time a wave is reflected and is thrown back at itself. In that case, a so-called standing wave is formed, with fixed points that never move called nodes. We will encounter this phenomenon in quantum mechanics at several points. Interference is also at the heart of one of the most famous experiments in all of physics, Young's double-slit experiment. When a wave goes through a slit that is roughly the size of its wavelength, it spreads out in all directions. We will try to understand why this spreading out happens in the next video, but for now we simply observe that this is what happens. Now, if you have two such slits in an otherwise impermeable wall, you will get two waves spreading out in a circular fashion, and those two will meet and interfere at several points in space. In certain directions, crests will always meet troughs and both waves will cancel out. You can see these areas very well in the wave pattern because the wave is really flat there. In other directions, crests will meet crests and interfere constructively, and you will get big waves, high intensities. When you perform this experiment with light, this means you will have places where the light is bright, the constructive interference, and you will get places where there is no light at all, the destructive interference. We will return to the double-slit experiment when discussing matter waves because it's such an important experiment showing the interference of waves. Also, historically, it was one of the key experiments showing the wave nature of light. A very interesting application of interference is interferometry. An interferometer is a device that can detect extremely small differences by observing the changes in an interference pattern. A popular example is the Michelson interferometer, which was used to disprove the ether more than 100 years ago, and also to detect gravitational waves in the 2010s. It basically works like this. Light, typically from a laser, is emitted at the source S and hits the beam splitter M. For example, a half-silvered mirror. The beam splitter does what its name suggests and splits the beam into two parts. One part of the beam passes through the mirror and moves along to point B, where it is reflected. The other part of the beam is reflected by the mirror and moves to point A and back. These two arms can be very long. For example, in the LIGO detector used for gravitational waves, they are 4 kilometers long. Additionally, the beams in LIGO were reflected in each arm several hundred times, so they would actually cover more than 1,000 kilometers. Both beams then pass through the beam splitter again and are collected at the detector in E, where they interfere, creating the telltale pattern. As this interference pattern is dependent on the phase of the laser light, even just a slight shift of a single wavelength will clearly change the interference pattern. This means that if the length of an arm of the interferometer is changed by just a single wavelength of the light, which is around 1/1000th of a millimeter, this will be detected. For the detection of gravitational waves, this experiment was performed at several labs at the same time, and then all of the results were combined together. And this way it was possible to discover even the inconceivably tiny oscillations caused by gravitational waves.
Too much interference.
Next time we will take a look at how waves propagate and what happens when they hit an obstacle. And with that, we will have learned almost everything we need to know about waves for quantum mechanics. If you have any questions or remarks, just let me know in the comments, and please like and subscribe, and see you next time.